In this problem, our goal is to determine the amount of torque generated around the axis of a bolt. And we're generating that torque using a force applied to this flex-headed ratchet wrench as shown in the figure. So the wrench is oriented the way it's shown with the 60-degree angle from the vertical. We've got a force applied perpendicular to the arm of that wrench. And the question is, what is the torque around the axis of the bolt? So this is a case where we've got kind of a 3D geometry here, and we have to sort through the R and the F that we're going to use in the R cross F part of the moment calculation, and then we have to sort out how we're going to figure out the component of that moment which is operating around the axis of the bolt. So there's a couple pieces to the puzzle here, and our approach is going to look like this. Step 1, we're going to define R and F, and what that's going to do is give us a way to calculate the moment around point A. The second thing we're going to do is project that moment onto the bolt axis, and that'll give us the moment around that bolt axis. So the process is reasonably straightforward here, but we do have some decisions to make, and some of those decisions impact how easy or difficult it's going to be to solve the problem. So before we start, let's look at one of those decisions we have to make, and that is how to set up the coordinate system. If we think about this a little bit, we want to choose a coordinate system that helps us in solving the problem by making it numerically easier to solve, by minimizing the algebra that we might want to do. So it seems like in this case it would be useful to define one axis of our coordinate system to be coincident with the axis of the bolt in which we are interested in. So I'm going to go ahead and define an axis this way. I'm going to call that the z-axis. And so that means the plane down at the bottom there where the bolt is going to have to be the xy plane. And the question is, how do we orient our xy plane such that we get an easier solution? And what I'm going to do is I'm going to define the x-axis to be acting out in this direction, and then by our right-handed coordinate system we're going to need a y-axis that kind of goes out this way somewhere. Now the reason I did that, the reason I oriented the x-axis the way I did, is because I want to make sure that on the negative x-axis that is where the arm of the wrench is. So in a sense, you're looking at the arm of that wrench being in the xz plane. So that makes it a lot easier to go ahead and define what the position vector is going to be. Okay? So with that said, now that we know something about the coordinate system, let's go ahead and define R and F. Let's look at R first. I'm going to do this in red. So we're going to define a position vector from A, where the origin of our coordinate system is, up here to where the force is applied. And so what we're really looking for is a position vector that looks like that. And we can define that as the sum of two other position vectors. One position vector that goes this way along the negative x-axis, and one that goes up this way towards the point of force application. Okay? So the way this is going to work is we're going to define R as having a couple of parts to it. It's going to have this first part, which is minus 0.75 in the I direction. And then to that, we're going to add another part. You can see that the length of the inclined part of the arm of the wrench is 10 inches. We know the angle is 60 degrees, so to that, we're going to be able to add a term that looks like this. It's going to be 10 inches. And the first part of this is going to be the sine of 60 degrees, and it's going to be in the negative I direction. And then the second part is going to be in the positive k direction. It's going to be the cosine of 60 degrees. Okay? And so when we add that all together, we end up with 10 times the sine of 60 plus 0.75 in the I direction, and that's negative, and then plus 10 times the cosine of 60 in the k direction, and that all has units of inches. Now if we define F, we've also got a coordinate system that makes it easy to define F. F is in the negative j direction. It's just minus 16 in the j. It's got units of pounds. Okay, so if we go back to the original figure, you can see that our y-axis was oriented in such a way that P is just in the negative x direction. Excuse me, the negative y direction. Okay, so now if we want to calculate the moment, we are going to go ahead and write ma is equal to r crossed with F. And I guess I should say I'm using the standard notation here, F for the force in our r cross F formulation, even though it's labeled as P in the figure. And when we do this, this is easy enough to write out. We can go ahead and write from the previous slide our statement for R, which was, let's see, minus 10 sine of 60 plus 0.75 in the I, and then it was plus 10 times the cosine of 60 in the K, and then we are going to do a cross product with minus 16 in the J. And when we do all the math, this turns out to be 150.6 in the K direction plus 80 in the I direction. And that has units of pound inches. So there's our moment around point A. Now what we need to do is go on to step 2, where we project that moment onto the bolt axis and determine the torque which we have available to loosen or tighten that bolt. So step 2 is to project onto the bolt axis. And the way we're going to do that is to identify a unit vector in the direction of the bolt axis. And again, by consulting our figure here, we notice that the bolt axis is right here in blue, and that happens to be coincident with the k-axis. Okay, so we're going to use the positive k-axis as our reference point there. And so when we make the calculation, the moment around the bolt axis is going to be ma dotted with the k unit vector, and what that really does is it just picks off the k component of the moment ma, and we end up with 150.6 pound-inches. Now you notice that the result here is a scalar because the dot product operation gives us a scalar value, and it says we have 150.6 pound-inches available to tighten or loosen the bolt depending upon which way we want to push it. Alright, let's go back to the beginning and kind of review. This was a problem where we were faced with a little bit of a choice up front about how to define the coordinate system, and we talked a bit about how to define it in such a way that made the calculations easier to do. Once we defined the coordinate system as shown, we defined R and F such that we could make our R cross F moment kind of calculation. Once we did that, we had to identify the bolt axis so that we could project that moment around point A onto the bolt axis and find the moment or the torque available to tighten or loosen the bolt. And there's your answer, 150.6 pound-inches.